Welcome back to our technical symposium for 2021. This is the last session of the day, and certainly the one that's been the most talked about so far, because it's had a bearing on many of the other presentations that we've had today. So we've had Ilan from Aeon Engineering, who I'm hoping will be watching this at some point in time because he's very interested. Also Ian Hall from Total Solutions, doing all of the truss engineering, and also Nick working on all of the things to do with standalone rigs and other things like that to get a good understanding. So it's very interesting to see what numbers people have a perception of even during the course of this technical symposium, where we're seeing different numbers being used as part of people's day-to-day calculations over time for real-world projects. So this is very exciting for us because it's new groundbreaking research and new information. So I'm very happy to be kicking this one off today. So remembering that we're on YouTube, I will be posing any of the questions that you raise here in the chat to Marion and passing them on there to her. Any of the information that we're posting up here after the event, we'll be organising all of this together here within Circus Rigging and Safety. And of course, just to say that this event particularly has been organised and supported in partnership with Articulation and Aerial Edge and funded by Creative Scotland. So thank you all for coming, and let's get started with this session where I can welcome back Marion for the last presentation you did here for us was a couple of months back, which was research which has been out there for a good period of time, but where you could actually put that into a lot of context for us so we could understand much more, not just about the maximal forces, but also about the perhaps busting some of the myths that we had about beginners versus advanced versus different sorts of things in that line. So first of all, welcome back, and thank you for being here.
Thank you. Hello, everyone.
Good. So I'm just going to switch and let you take this on, because we'd definitely like to hear more about you, about your research, and definitely about this program. So please feel free to take it away.
Thank you. Thank you so much. So I'm going to share my screen. Is everything okay?
Yep, very good.
Perfect. Thank you so much. Thank you. So today I'm going to present my last research. So I measured the maximal dynamic forces in 10 circus disciplines. So new results. I'm so excited about it. First, I will present the CRITAC. The CRITAC is the research center I'm working. So it's a center for research, innovation, and transfers in circus arts. We are based in Montreal. So what do we do? So the mission of the CRITAC is to advance human potential and performance. So it's a bit larger than circus. We also are working with living performance, living arts. And so we want to support research and innovation in Quebec. So we are working not only in engineering, as I do, but also in many other areas, as you can see. So we have areas of focus on the body, on psychological, on social, and also creativity. We are working with lots of different researchers. And the areas of intervention. So of course, we are working in innovation and body techniques, equipment, and performance environments. This is where I mostly do my work. But we have also areas in the interactive and immersive technologies in circus arts, also health and safety, and also pedagogy, writing, narrating, aesthetic, a lot of fun and exciting research. So it's not only technical, that's what we are doing. What do we offer? So we offer 3 kinds of service, which is applied research, technical assistance, and information and training. So depending of for example, the acrobats or the person that come to us, we have different kind of service. So for example, for applied research, I can try to set up a new research protocol, do some tests, do some experiments, and do some analysis. Or we can also help circus companies with technical issues. So for example, I do some structural analysis for some structure, and also information and training. So as you can see, I'm also giving conferences and any kind of training that we are asked. And we are working with a lot of partners. So we are working, of course, with industries. So the most known, I think, is Cirque du Soleil and the Seven Fingers, but we're also working with a lot of different circus companies, also institutions. So for example, the Toru, which is a show hall in Montreal that can do circus. We are working with a lot of universities, of course, and also associations. And that's me. So this is me this summer during the measurements. At the last day, we took some pictures. As you can see, it's fun. It's fun to take measurements. So this is me. I'm an engineer of research. So I did a master's degree in mechanical engineering at Polytechnic, and I will show you my project. I already talked about it, but I will just, for some of you that weren't there at the interview with Mark, I will present the results I found. And today I'm finishing my PhD. I did the PhD in biomedical engineering, and I'm mostly doing biomechanics. And also I will show you some of the results today. And I'm employee of the CRITAC since 2017 now, but I've been working in the circus industry for now it's been almost 10 years. And before that, I was working in the entertainment industry, mostly theater company. So I did a lot of structural analysis. Also, I help technical directors to design any kind of scenery equipment, for example. Okay, so what do we do at the CRITAC? We, as I said, I'm part of the department of design of equipment, but we also do design of performance environments. So, for example, I will show you just 3 examples to what we are doing. But as I said, we are doing a lot of other projects. But just to give you an example to what we are doing. So, first of all, we are helping a future circus school. So they bought a church and they want to design a structure inside the church to support circus equipment. So we don't want to make holes or to dig into the structure of the church. So we come up with a structure inside that really is really the same shape of the church, and to be able to support any kind of circus equipment. So this is the kind of project that we are doing, for example. Another one, just to show you some design, is a rotative teeterboard. So a Korean teeterboard, they wanted the base to be rotative. You can see we did the engineering, the design, and on the right, the pictures on the right at the final equipment. So it's all electronically commanded, so they can block or do the rotation of the teeterboard with a command. And so that the goal for this is to have a show only on teeterboards, and they can switch the angle, the direction of the teeterboard to have different perspective, for the audience to have different perspective. So for example, if you have the 2 acrobats in line or in diagonal, you can have a different perspective on the performance. And another one, so this is one of my projects, this one. So we worked a bit about tensegrity. So I don't know if you know this principle, but tensegrity is really amazing. If you just Google that, you will see amazing shape. It's really, I don't know, out of space, I would say. So you can build really a floating structure that doesn't look real. And so there is a troupe of circus of acrobats, and they came to me and asked to build a tensegrity structure. So at first they wanted to have this kind of structure. So on the left you can see, so it's the self-supported structure, and I don't know if you saw some of them in your social media, but it was really popular. You can build a chair or a table based on this structure. So the structure is holding by itself. There is no cable outside, and you can put some weight on top of that. So it was unreal. And what they asked is that they wanted a structure of 6 meters high, which was not, it was a big challenge. So we designed on the right, we designed the structure, and we didn't know if it was possible to have this structure this high. So we wanted to try. So the first idea was to just rent some truss and to just like a Lego, to just assemble them and see what we are doing, what we are able to do with that. But unfortunately, we also made a 3D model in finite elements to be sure that it is strong enough to support the acrobats. And so the structure in itself can hold, but as soon as you put loads on top of them, and what the acrobats wanted to do is to come on top of the structure and do acrobatic on top. And as soon as you do asymmetrical loads, the structure unbalanced and falls. So we did not pursue this kind of structure, but we came to another tensegrity structure, and maybe a more simpler one. So it looks like this. It's only, I could say it's only 3 tubes, so 3 beams. So the goal was to have 2 trusses and 1 pole, like a Chinese pole, to be able to do some kind of movement like that look like in a Chinese pole. And also the structure is only holding by cables, and they can do a lot of things. So they can do, as you can see, they can hold it on the floor like this. They can climb on it. They can also use the cable to do tight wire performance. And also what they are doing, and they have a structure to hang the structure and make it rotate. So I will show you a videos of what it looks like. Sorry, I need to. Like this, do you see?
Yeah, we can see that.
Yes. Okay, so here we go. So yeah, it was a fun and interesting project. And in fact, integrity structure are not that easy to incorporate into circus performance. So it was a bit of a challenge because, as you know, like circus performance generates dynamic forces, and they want so this kind of structure is not designed to have external loads. So it was kind of a challenge to design it, to build it. So the topic of today, forces in circus performance. So I will just start by show you what I already done. So as I said, I did a master's degree, and during my master's degree, my research project was to measure the dynamic forces in 5 aerial disciplines. So I already talked a bit in the interview with Mark, but I will show you the main results here just to be sure that everybody knows it. So the 5 aerial disciplines were aerial hoop, aerial straps, rope, silk, and then trapeze. In this study, I had 16 students of the National Circus Schools of Montreal, and I measured more than 300 movements. With these results, I published 2 papers. As you can see the title. If you want the 2 publications, because you can only find the abstract on internet, but if you want the full publication with everything, the full results and the full conclusion, you can just write to me and I will send it to you. It will be my pleasure. And the maximum force. So it's so the maximal force here are presented in body weight. So the maximum force I measured was in aerial straps. It was 8 times the body weight. Rope, we had 5 times the body weight. Then trapeze and silk 5 times. And aerial hoop was 3 times. So in aerial hoop, I only had the participant that did mostly contortions. So the measurement I had was maybe not the best one in dynamic. If you want dynamic forces. So that's what also the generated my new project of this summer that I will present. Just a few examples. So the force will appear on the left, and at the same time it's synchronized. The movement will run on the right. So you have to look at the right and left at the same time. Be ready. Let's go. So it's a slack drop in rope. The red line is the weight of the acrobat. And you can see at the beginning, when the acrobat is mostly static, when is waiting, the measurement, the force I measured was the weight of the acrobat. And as soon as it's doing movement, the forces will have a different value. So it could be less, it could be 0 when there is no tension force. So when it's in a free fall, the force is 0, and during the impact you can see the big peak. So in this movement, for example, it generated you can see 900 livres. So it's not in Newton because here we don't use Newton. I don't know in UK what, or in Scottish what do you use, but here in Montreal they prefer to have the forces in livres. But also I will present the results in both in Newton and also another movement. So it's in strap. So the movement is called a dislock. Up again, the red line is the weight of the acrobats. Oh, I will just stop right there because, oh, okay, no, I can't. So as you can see, there is 2 peaks in this movement. The first one is when the acrobat is kicking his leg outside, and after that, the bigger one is when is coming through the vertical, because you have all of the tension force, all of the momentum that is coming, yeah. So the maximum forces I measured in straps was continuous dislock. I don't know how to say it in English. but it's when he's doing 3 dislock and he's keeping a straight body. At each dislock, it will increase in his forces, and at the 3rd time, that's when I measured the maximal forces. Fall in silk. So in this movement, we can see she generated almost 600 livres. And you can see the difference between rope and silk is mostly due to the elasticity of the equipment. The rope is more rigid than the silk, so of course the forces that they will generate is different. The silk will be less than the in rope. So this summer, here we come, new projects. So as you can see, I measured, but only we can say only 5 aerial disciplines, but there were so many more disciplines that we did not have the measurements, and we wanted to take the measurements. And as I said, there were some limits in my project. So for example, in aerial hoop. And also, I didn't talk about it, but the sampling frequency, I used 100 heads, so it's 100 measurements per second. And some of people said to me that maybe was not enough. So based on that, I set up a new project this summer, and we measured a lot of different disciplines. So here we come. So first one, Chinese pole. So what I did is that I had load cells at each cable, as you can see in pink. So as you can see, the Chinese pole was a bit asymmetrical in the rigging. We had 2 cables that were coming from the right and 1 from the left. So we already knew that the forces won't be identical in the 3 cables, but that is also a good example of this kind of setup. And but you can see, for example, the picture on the right of the load cell I used. And I also had at the base on the ground between the Chinese pole and the ground, I had a load cell that measured compression, so the forces of compression on the ground. Next, so every single point setup. So we had a rope, a flying pole, and silk, I think, if I remember correctly. So it's the same as the last one. We had 1 load cell, and we had a transmitter that worked in Wi-Fi to transmit the data live on the computer, because we couldn't have a cable that run through the rigging, because when the acrobat is turning on doing movements, so we couldn't afford to have the cable being stuck. So we had everything in Wi-Fi. And for this setup, for the silk, we measured 3 kinds of elasticity of silk. So we had a very elastic one, a medium elastic, and a rigid silk. So it was good to know the difference between different elasticity of silk. So I don't know also what you are using in Europe. Here in Montreal, I would say in the past few years, they were using very elastic silk, but more and more the acrobat are using medium elastic, I would say, and some of them rigid. It really depends on the kind of performance that they want to achieve. And trapeze, so we had the swinging trapeze, fixed solo trapeze, and fixed duo trapeze. So the picture is also only the swinging trapeze. I had 2 load cells on the rope of the swinging trapeze. So for the swinging trapeze, we shortened the rope to have the exact length that the acrobat are used to, because if not, the acrobats couldn't do the movement that because there is a precise timing in the swinging, so we didn't want to affect the performance, because even with the load cell, there is some weight, so the timing was a bit different. So we really wanted to have the right length for the acrobat to not be disturbed so much. And tightwire, also we had the load cell. So the load cell are different for each setup, because the maximum value that we recorded was different. So with the maximum forces that each load cell could record was different. So for example, this one could go up to 10,000 livres, if I remember correctly. In Chinese pole, for example, we use a smaller load cell. And the sampling frequency for all of the setups was 2000 hertz. So this time we have good enough samples, I'm pretty sure. And for tightwire, we had two kinds of tightwire. We had this one, which is 1 meter, 1.5 meter high, if I remember correctly. And one of the acrobats wanted to do salto, somersault, salto. And we used a smaller tightwire to be sure, like with mattress and everything. And Korean teeterboard. So I'm doing a PhD, finishing my PhD, almost done, 1 month left. So my PhD was about Korean teeterboard, and I did some measurements, mostly in biomechanics. I did some measurements in the movement with motion capture. I don't know if you know motion capture. It's the one that I don't know if some picture or some videos in cinema, you know, with the white markers everywhere on the body. So you can record everything, every position, angles, speed of every part of the body. So I could measure everything that the acrobat are doing at all time. And also what I did, I also put markers on the teeterboard, so I could record the deformation and the movement of the teeterboard. And last part was muscle. I also had sensors of the muscle activity on the legs of the acrobats. And this one that I'm presenting to you is the impact forces. So in biomechanics, what they usually use for measurements is force platform. So it's like a rectangular platform that you put on the ground, and when you're working on or running on it, it measures the forces, the vertical forces. But in Korean teeterboard, I couldn't put a force platform on a teeterboard, as you can understand. So I use a pressure sensor insoles. So you put them inside the shoes, as you can see on the left, and it records the pressure that could be transformed into vertical forces. So I will present you some of that in today. And for Korean teeterboard, I asked the participant to do different kind of landing. So I had the pushing technique. Again, I don't know what you are using in Europe, but in Montreal, what they are teaching and doing, the acrobat, is a pushing technique. So what is the pushing technique? Is that it consists at bending the knees before touching the teeterboard. And during the rotation of the teeterboard to the mat, they push. It means they extend their legs until they are straight on the mat. One of the other techniques that we can have is straight legs. So it means that the acrobats keep straight legs during landing. And the last one is a dead board. So in French, it's called planche vide, empty board. So sometimes I will use this term, I'm sorry, but I know now that acrobats are using the term dead board, which is really joyful, always with the metaphoric images in circus, I would say. So dead board, it means that when you have one of the acrobat that is in the air, and for example, he falls and he can't keep his balance, or he's falling outside. He roll backside, for example, backward, and the other acrobat is in the air, and he will land on a teeterboard that is empty, because there is no one. The other acrobat is outside. So it will have a strong impact, direct full impact, because there is no counterweight. The other acrobat is not here to do the counterweight to have a resistance during landing. So sometimes you can see the teachers that they launch mats to just have some weight on the teeterboard to have this kind of resistance. So I had 4 participants doing these 3 kinds of landing. So in total, I had 39 acrobats, 28 professionals, and 11 students of the National Circus School of Montreal. And in total, I had more than almost 900 movements recorded. I have almost 300 from Korean teeterboard, so there is less for each discipline. And you have the details of the number of acrobats in each disciplines. So we have 5 in Chinese pole area, hoop and rope. We have 2 in silk and flying pole. Only 2 in silk because I already did the measurements and I just wanted the difference between 3 kinds of elasticity. 2 in flying pole because I couldn't find more. 4 in swinging trapeze, 3 in solo fixed trapeze, 2 duos, so 4 acrobats in duo fixed trapeze, and 4 in tightwire and Korean teeterboard. So also how we did the measurement. So apart from Korean teeterboard that was part of my PhD, so the setup, the protocol was a bit different. But for all other disciplines, how did we do that? So I asked the teacher of the National Circus School to come up with 4 kinds of movement that was, I would say, classical or standard that could be repeated for everyone, and that we knew or we think that it will generate high forces. So for these 4 movements, each participant was asked to repeat 4 times, because in science we need to have a lot of data to do statistical analysis. And after that, after this 4 repetition of 4 movements, the acrobats could do anything that they wanted, and they could do it once. Sometimes they wanted to repeat it, but we just asked to have 1 measurement. And just, for example, so we asked the acrobats sometimes to do a movement that are unique to them, or for example, to have, they have a movement that they know generates a lot on the body, and they want to know the value. So that's what, and it was free at this time. Results. Here we are. So here is a tight wire and Chinese pole. So tight wire, we had a pretension of 2,040 livres, and the maximal forces was 3,000 and almost 400. So it means that we have 1,400 more than the pretension, and in kilonewton is 15 kilonewton. And the movement that generated the highest force was the somersault. I don't remember, Mark, do we have the video of this one?
Sorry, the somersault on Chinese pole? I believe we did.
No, it's Chinese pole.
Oh, sorry, the Chinese pole or the...
This one is the contact. So the contact was the movement that generated the highest forces in Chinese pole.
Which one would you like?
So we can see the compression. We had the pretension, pre-compression, I would say, on the floor of so why the minus? Because the compression and engineering and have tension that's worse and the maximum force was 1,400, which means that we almost 1,000 in addition. And the Chinese pole in the fifth table, as you can see, the tendency was the one that had a highest force, and it was the one that was alone on the right side and the maximum force was 600 Not a lot, but we expected this kind of.
Can you switch the mic?
Yes. Thank you. So, yeah. Oh, tightwire. Here we go. So, here's some. Yes, this one. Yes, thank you. So, more results? Yes.
So I realised I was on mute to you, although everybody else could hear me.
Okay.
My apologies.
You were talking to the laptop.
Yeah, there we go.
Okay, so more results. So aerial hoop, this time the maximal forces I measured was 5 body weight. So if you remember in 2015, I measured 3 times. So it was a big difference. So it was a good thing to do it again. And this time we had more dynamic movement, so that explains the difference. And the movement was a drop, hip, circle to front bounce. I hope I had the names right because the name was given in French, so I had to translate them, but I'm really not sure. So maybe a video would be great next time. Yes. And after that we go. Also, so in my last I don't know if you can come back to yes. So rope again, the maximum process I had in 2015 was 6 times. So this time also we had a difference, which was 7.3 times the weight, the body weight of the acrobat. Also for a slide drop. And the silk, the 3 different silk. So as you can see, the silk the elastic one, the forces was 540, medium elastic was 590, and rigid silk was 680. So almost 100 livres for each different elasticity. And the 3 movement was slack drop again. It was always slack drop. Next one we have flying pole. So the maximum forces was 4 body weights for a movement called bisect to back salto. It was a bit unexpected because when I wanted to do flying pole, the teachers and the acrobats said, "Oh no, it doesn't generate high forces because it's not as dynamic," and it was a bit of a surprise. To have this kind of forces in our results. Mark, I think we have also a video of this one. Yes, thank you. And next one we have swinging trapeze. Swing trapeze, so movement is called So the measurement, the forces was 5.6 times the 21. So how it was calculated. So we add the two load cells, and after that we divide it by the weight of the acrobat. So it could be unbalanced if, for example, if the acrobat is more closer to one of the rope, but the total is 5.6 times the body weight. Next one, we have a solo fixed trapeze, which was 6.8 times for movement for cross back slide drop. And you can see on the videos on the right is my intern. So I was not alone this summer to do the measurement. I had an intern from Polytechnique Montreal that helped me do all of the measurements. And last one is the trapeze. So it's movement for big tempo back salto. So the maximal forces for dual trapeze was 2.5 body weight, and how we calculated it, we had the two load cells as in other trapeze discipline, but we divided by the sum of the weights of the two acrobats. So the total was not a lot, 2.5 body weights, and I'm pretty sure the forces that they generate are still high. It's just that there is another connection because you have the two performers, and I'm pretty sure they how do you say? The forces are between the two acrobats and not between the trapeze and the rigging parts. Yeah. I hope it's clear.
No, it's very clear to me. Yes, it's very good.
Thank you. And last one, so Korean teeterboard. So the maximal forces were 13.5, but also in deadboard 13 times. So it's really gigantic, I would say, times the body weight. And for the pushing technique was 9 times the body weight. I know that the deadboards are movements that have precautions, are dangerous, and the performance, the students or the acrobats in Korean teeterboard, they don't like to do this when it happens. They don't like to do this movement. That's why they're always rushing on the teeterboard when someone falls backward to have this resistance, this counter weight. And now we know why, because the forces are really, really high on the body. And so, conclusion. So I hope that this data will help the designer and riggers and the circus community to have a safer environment and safer design of equipment. I just want you to remind that the measurement I did was at the National Circus School with you saw it, the 40 acrobats. So if we have different location, different movement, different acrobats, different disciplines, the movement, the forces generated will be different. So don't take this data maybe for, but you can take this data to help you in your calculation, but you have to adapt it to your situation. And also I would like to remind you that it was maximal values. It means that it is extreme values, but in fact, it's different than average values. If you take the maximal forces in average, it's not as high. For example, the 13 times the body weight in Korean teeterboard, they did not generate this force each time that they did a deadboard. It was one extreme value. So, yes, so I just want to remind you this. And the last question I would ask is maybe the link with the body. So what do we know about workload on the body? How do we do how do we link the forces I measure to the body, and maybe after that the next question would be how to adapt preparation, training, and shows when we know the workload on the body or on the acrobats. So what's next with this data? So I have my from PhD in Korean teeterboard. I have one paper that I think is accepted now in the Journal of Sports Engineering and Technology about impact forces I presented to you. I also, in fact, this paper is much more than just presenting the maximal forces. I looked at the effect of jump height, landing technique, participants, and teeterboard, because I had 3 different teeterboards. So is there a difference in forces and also in loading rates with these parameters? And in my PhD, I also have 2 author papers that are coming. One about the kinematic, the movement of the acrobats, and the other one is about what I call the recall effects. As I said, that the teeterboard is not rigid, it's just not the plank. It has a deformation effect, and the acrobat are using what they are calling a whip, what I called in more engineering terms, the recall effect, to help them, to catapult them into the air. And also with this data, I'm trying to finish a paper. I don't know, I still don't know the title, but it would look like something like Maximal dynamic forces exerted by acrobats in a circus apparatus. I'm still working on the further analysis, statistical analysis, but I don't want just to show to present maximum forces. I also want to do statistical analysis, and I'm still undecided to what to do. So maybe I could talk a bit about that if you have any suggestion for me. I'm still undecided to do the difference between acrobats, or the variability in acrobats, or the difference in movements. So I have all of this graphics, all of this data, and I'm still trying to figure which one would be the best. And also we are working here at the CRITAC on, it's called Guide d'aménagement des espaces de formation et des équipements circassiens. So the ministry here in Canada asked us to work on the guidelines for a circus art safety space. So if you want to have a school or a circus performance or practice, what do we need? What the space, the equipment, the mats, the floor, the lights, everything. So everything is, all of the recommendation will be in this document, and the maximal results will be also in this document, because it could help riggers and designer for safety. That's it for me. Thank you for your attention. If you have any question, please do not hesitate. I also write my email if you have any question, if you want to have some of the paper, I talked about it. And also I have a website, so please contact me. It will be my pleasure to answer your questions.
Thank you very much, Marion. So, and thanks for coming and joining us today and presenting us all of that hard work and research. There's a couple of areas there that you're doing what we would see as like really important work for the development of the sector. First of those is certainly in the impact on the equipment and the rigging to better understand the forces. So you're the one person who's actually done the most amount of research that that we've come across in acrobatic forces on equipment. So for me, that's been fundamental in taking that conversation forwards, and us understanding that if we want to take those maximal forces into consideration, then somewhere between 5 times and 8 times body weight is what we're looking at. And if I refer people back to your last session, but also your 2017 paper, it also looks at comparatively what the factor of safety is on the equipment itself, like silks and like hoop and like straps, as well as on that rigging point, which is something which is like I see as really important. The other thing that you're looking at there is the effect on the performer, which is also really the next level beyond that. So if we're into safe practice and safe teaching and artist development, then that's certainly an area that getting an understanding of how training and conditioning will improve the artist's ability to resist or to work with those forces. Because certainly if we were looking at the example of the dislocation on straps, then there's a certain amount of physical conditioning which takes place to be able to get that 8 times body weight. Because as a beginner or even as an intermediate level student of a year or two, it would put a lot of force through the shoulders if they weren't conditioned appropriately to do that.
Yeah, I think so. Yeah.
Yeah, so I'm really interested in the work from a teaching perspective, but also from your figures, I was shocked by how much force was put on Korean teeterboard, because out of the disciplines that I practice of solo trapeze and doubles trapeze, it's actually Korean teeterboard where I busted my ankle really badly for several months at a time. So looking at those forces, even though not doing it at the same level as the acrobats at ENC would be doing it, there's a lot more force being put through ankles and things like that, which is really interesting.
We have to remember that they are jumping at the height of 3 to 5 with 3 to 5 meters, so it's not it's really hard.
Yeah, yes. One thing on the doubles trapeze, because if we're talking it's 2.5 times body weight, which is the force that's actually being measured, if we're looking at that from an artist perspective, the force which is being generated by a smaller flyer on the shoulders of the heavier base, then the forces that are being applied to the shoulders of the base are actually quite considerable in there where you're doing that catching.
Yes.
Because the body weight calculations are based around both base and flyer together.
Yes, exactly. Yeah, and I'm pretty sure that the person that is holding the performer is absorbing, in fact, the forces in the shoulder. So I'm pretty sure if we want to look at what is happening on the body of both performers, I'm pretty sure they generate really high forces. It's just not transmitted to the rigging force. Yeah. Because it's one of the more demanding discipline. Fixed trapeze, yes.
Yeah. If I'm looking at injuries which come from doubles trapeze from bad posture, like with the artists holding themselves in a more sort of spinal arch looking down there, then I'm seeing neck injuries and lower back injuries from those sorts of forces, even more so than shoulder injuries.
Yeah, that's true. Yeah.
Very interesting. So you're looking at your next research adventure, and you've got some options which you've just sort of mentioned there. So if there's I'm very keen to see more data continuing to be collected on the forces to do on the rigging, but I think that you've gone quite a long way down that road, and there's certainly more data that can always be collected and more information, because even just this summer, and you understood that with Lyra there was a lack of data, because you knew that the forces that you'd been collecting so far were to do mainly with contortion on hoop. And seeing what you've been able to do here brings the level of hoop back up to that, similar to that of silks. So where we're looking at sort of almost 5 times body weight.
Yeah, and also I was wondering if there is I don't know, an increase in the technical performance that we are doing now versus compared to what they were doing, I don't know, 15 or 20 years ago. I don't know if there is a difference. I'm not an expert on this area, but because there were some measurements in France, I think it's 15 or 20 years ago, and it was a bit less than what I measured. So I was wondering if maybe it's in the movement that that they are doing now, the acrobats. But this is not my expertise.
Just anecdotally, I would say that from talking to teachers and riggers, they're seeing forces increasing over time as acrobatic technique improves. They're able to pull off bigger tricks and techniques, and as training techniques improve, we're able to condition bodies better to be able to take those forces. Have you any interest or ability to look at things like breaks to lay out on flying trapeze to see the sort of forces there? Because that's something that at the bottom of that pendulum is where you're also adding to the force to get the height to be able to do the techniques. I think you'd see some of that in swinging trapeze, but I think in flying trapeze it's particularly interesting.
Yeah, it would be really interesting to have these measurements. We do not have currently the space here in National Circus Hall to do flying trapeze, so that's why I did not have these measurements. Yeah. I know that the School of Quebec have flying trapeze, so I need to go there. But yeah, it would be really, really interesting. Also, yeah, for the swinging trapeze, as I said, I did not analyze the data in depth, so I don't know at which time it happened. Yeah. And also, I just have the maximal forces right now. I'm still trying to figure and to look at all of the data, so I don't have the answer, sorry.
No problem. Are you looking at publishing the data itself beyond what's going into the paper for further analysis, or what's your thinking about data collection for the future?
No, in this paper I will present the result I just showed you, so the maximal forces and also a statistical analysis. Yeah. And for further measurements, I don't know. I don't have any plan for after that. I have many projects, but not related to dynamic forces.
Because if we're looking at technique and analysing technique, both on the artist and on the equipment itself, it could be quite instructive to be able to look at individual techniques, see where the forces are being delivered, and what the impact of that is on the trick itself as well as on the acrobat.
Yeah, that's true. I will take some notes.
Sorry. Just if you're looking at the development of technique, then when and how you apply a force has a resultant effect on the technique itself. So I think that would be, for future research, something interesting to look at on a per discipline basis, because I'd not, throwing people around on double trapeze, I'd not noticed, not understood that level of forces. We're looking at it and going 2.5 is not very high, but it is on the performers. So this for me has been a really interesting set of research, and to be able to take that further would be good. And certainly understanding the forces on the people themselves for me would be the next interesting piece of research. So fantastic. So I've got lots of things coming up. There's lots of comments here, or a few comments that people have been making, but most of all, it's really thank you very much, and it's really interesting. Those I haven't seen much in the way of further questions apart from comments about my technical skills at keeping the audio going. But thank you, and thank you again for coming and presenting your information here. That's really good to see. And please keep us advised of further developments. I hope you'll be happy if I host some of your papers here that people can download, if that's okay as well. So I'll put those up on the site in the next week or so, once we've finished collating all of these videos together.
Perfect. Thank you so much.
Thank you so much. I really appreciate it. That's wonderful. Thank you.
Thank you.
So thanks to everybody for attending today, and that's the last session for today. We've got 4 more sessions tomorrow. We're going to start out with Line Grip's Line Scale 3, the new load cell that they're releasing in the next wee while. I think that was a crowd-funded effort, but we'll hear more from Andy on that tomorrow. We'll also be looking at the Arcadia's Metamorphosis show, and how that came together. We'll be looking at creative rigging with No Fit State Circus with Lyndall Murray, and we'll have stunt rigging for circus shows with Brett Copes. One on loads and engineering and 3 on show rigging for tomorrow. So come along and see those. It's going to be also an interesting day. So thank you very much and see you all tomorrow.